Hi there, everybody. So, my name is Python Surana, and I'm an instructor at Developmentor. So today we're going to be talking about a really complicated new library that is out for Python 3.4, although they're still working on it, and it's called Async IO. If during the talk you have any questions, please feel free to type them in the questions panel on your GoToWebinar screen, and whenever I spot them, I'll try to answer them. Okay, so the issue here is how to do asynchronous programming in Python. Oops. All right, so the question is, why would you want to do this? So remember that Python is a single-threaded runtime, or at least the CPython implementation is. If you were to run Python on Java or .NET, then you would have access to multiple threads, and you wouldn't have this problem. But that's not really the standard runtime. So for the CPython implementation, there's only a single thread, and that's not going to change ever. So if that thread makes a call to something where it blocks, then your entire program stops, right? So this happens a lot whenever you're writing something that interacts with I/O, usually with network calls, which, by the way, includes web service calls and database calls, because all of those are going over the socket. It also happens with file I/O, because your drives are your hard drive is much slower than your CPU. So that's another area where your program basically comes to a screeching halt, waiting for the operating system to return with something, and then your program can continue. All right. So in order to make use of these sort of asynchronous operations, it does require operating system support. And so there's a little bit of difference, well, let's say there's a fair bit of difference between the way a Unix system works and Windows works. And so what you'll find is that the support for Windows asynchronous calls are a little bit lacking in the current implementation, but hopefully that'll improve over time. Now, if you can write code that uses these sorts of asynchronous operations, so that means you say, I want to read from a socket, and then instead of blocking, waiting for something to arrive on the socket, you go and do something else. And whenever the operating system says, hey, I've got something on the socket, then you can execute the code you were going to run, right? So by writing your code that way, what you do is you enable concurrency, which is actually different from parallelism. Parallelism means actually making use of all the cores and processors on your machine. So when you run 4 threads at the same time on 4 separate cores, then that's parallelism. But of course, we can't really achieve that with a single Python process. So concurrency, what that means is splitting up your program into independent pieces that can be scheduled to run in any order. It can still run on a single thread. And that's exactly what Python does, and that's also what Node does. So you can sometimes get concurrency to work with parallelism in Python using the multiprocessing library. And so that's a nice little blend between the two. So of course, these asynchronous calls require runtime support, as we'll see later. The other problem with asynchronous programming is that it's very difficult to program, and we'll see, in fact, that the async IO library in Python is a real pain. It's a little bit easier if you have language support, and we'll see that Python 3.5 will add something to help out with that. The button doesn't work. All right, so people have been doing asynchronous programming in Python for quite a while. There are implementations that have been running on Python 2 and 3. The most popular are the first three, Twisted, Tornado, and Eventlets, or gEvent. So these things have their own, API and all that, but they're basically running the same way that Async IO does. Oftentimes people try to write their own custom code, but that is just super painful. All right, so the Async IO library right now they call it provisional in Python 3.4. They said they're still, they still might change things, but it should be final when 3.5 comes out. What they're hoping to do is, there's a quote somewhere where Guido says something like, I'm not trying to reinvent the wheel, I'm trying to build a better wheel. I think he was talking about this. And so basically there already exist these async libraries, which we saw here. He's not trying to reinvent something new. Instead, he wants to write a library, a single library that encompasses what these three can do. But by having a clean API, then you can build more sophisticated things on top of the Async IO library. Now, the core to making async work is getting a notification from the operating system when some event has occurred, right? Python can't do it, and so we need support from the OS. So there is another library which is lower level than Async IO, called selectors. And with selectors, they do use things like select, poll, and epoll on Unix, and I think they have some support for Windows, where, as I said, you register a whole bunch of file handles or sockets or signal handlers or whatever, and you say, okay, whenever one of those things is available, let me know. So you set up these callbacks, right? All of that is handled by the selectors library, and Async IO will use that. Windows has something called IO completion ports, which is actually much, much fancier and perhaps better. But the Python people are all Unix people, and they do have support for this in Async IO if you choose the right event loop. But it's from what I've been reading, it's a little bit sort of a partial implementation. So there's still quite a few things in Windows that are not supported by this library. And then finally, the Async IO library, as we'll see, is kind of low level, and it's difficult to use. And really, what you want to do is hope that somebody builds their library on top of Async IO, and you can therefore use that library. Okay, and I'll show you one example a little bit later. Oh, well, actually, I can just click on this and show you. So over at this link, asyncio.org, what they're trying to do is pull together libraries that currently sit on top of Async IO. So here, for example, is an asynchronous access to a Postgres database. Here's access to a 0MQ queue, Memcache, Redis. This one I'll show you later on. DNS, webs, and so on, right? Here's a Mongo database right here, and so on. So there are all these libraries where, they're much higher level, and they achieve asynchronous processing by running on top of Async IO. So when it comes to programming, you would really rather use one of these libraries and not mess around with Async IO directly. Okay, so the architecture of the async IO stuff is, in the most simplistic way, the main thing is there's an event loop. So that, with Python, there's only one thread. Well, that thread is going to be running the event loop. And the event loop is basically looking for any of the events that occur, whether it's signaled by the operating system. There's another API where they can actually use a thread pool, Python's thread pool, to maybe be signaled when something happens. But somehow it'll be signaled when something happens. When that thing occurs, it will call into this next level, the coroutine, feature, or task. Okay? So and I'll define these terms later on. But this is where your actual code will be represented. So if you want to process some input that comes on a socket, if you want to read a file, whatever it is, it'll be represented in this thing. But in order to perform those I/O operations, that requires this bit on the bottom, the transport and the protocol, which I'll define later on. Okay, but this is actually dealing with the different I/O, systems. All right, so I'm not really good at drawing things on a slide, but this will hopefully give you an idea. So this event loop is sitting here waiting, monitoring a bunch of events. Whenever the event is signaled, for every event, there's going to be a pointer to some kind of coroutine. So the event loop, remember, it's just a single thread. It gets notified that something happens, and therefore it makes a blocking call to the coroutine. At this point, the event loop, that one thread is totally, stuck doing your work in the coroutine, which is totally fine. It's doing that work. However, there's no way for it to yank it back. In an operating system, sorry, somebody's riding by on a riding lawnmower. So for a normal operating system, they have what's called preemptive multitasking, which means that the operating system will force a thread to give up the core, give up the processor, and then schedule another thread on there. This thing is called cooperative multitasking, which means when you run a coroutine, nothing can interrupt it, and it's up to the coroutine to yield back time, or basically to give control back to the event loop. Okay? There's a question about how to run the event loop. Yeah, we'll get there. But first, let's just understand what's happening. Okay? So the control flow goes to the coroutine. The coroutine that's what the code you're going to write, so it does all the work, and then it has to give up control back to the event loop. However, what if you're not finished yet, right? Because you need to do 20 steps, 30 steps. So what you do is like 1 or 2 steps, and then you would give back control, and then the event loop knows that the coroutine is not done, but it monitors to see if there's something else that needs to be done. And if there is, let's say there's 2 things that need to get done, it calls the second guy. This guy will do whatever work it needs to do, and then hopefully yield back to the event loop. And now the event loop knows that there are 2 coroutines running. They're not finished yet, so it calls the first one. Coroutine does a little bit more work and yields back. Calls the second coroutine. It does a little bit more work and yields back. Okay? Whenever one of these coroutines is finished, then the event loop will know that this thing is done and remove it and continue processing whatever is left over. Okay? So that's essentially what's happening. It's all running on a single thread, and the only cool thing is that it monitors these events so that once the event is triggered, it knows to call your coroutine. All right. So there's only going to be one event loop in your program, and you can use it. Typically, you would just use the default event loop. There are a few others that you can choose, but that's a little bit more complicated. So it's good enough to just say get event loop to get your default loop. All right. in this event loop, you have to register what is going to execute, which we'll see in the code examples. All right, and then you have to run the event loop. And once the event loop is running, that triggers, this drawing that I showed you earlier. All right. So I use this term coroutine. So if you think about a normal function call, you call it, and then it returns one value, and then it's finished, right? It can only return one value, and then it's done. A coroutine is a generalized function, which means you can call it, and it can return more than one value. Like it can just keep returning values, and every time it returns a value, then you can just tell the coroutine, okay, give me the next value, and it goes back, and so the coroutine remembers where it was in the processing and continues from there. And once it finds an interesting value, it returns it. Okay, so a coroutine is something that is like a function that can keep returning values, and you just say, okay, I got a value, so what's the next one? And it runs a little bit more and returns another value. Okay, so in Async IO, you're going to use the yield from command, which is a way of delegating to another generator to yield control out of the coroutine. Okay, and so you can use yield from inside any function, but Async IO requires that you add a little decorator to your function that says this is a coroutine. All right. So once you have a coroutine, they have a thing called a future. A future. So you can take a coroutine and convert it into a future, and a future is just something that says it kind of monitors the execution of the coroutine. Okay, a future is a very old term in computer science. It says there's some task that may or may not be running, and the result, you can get the result sometime in the future. Okay, so it's kind of like if you start a job and then you come back 10 minutes later and say, okay, what's the result? That's what a future is. This future is an abstract class. I think it's abstract. And there's a subclass called task. The task is the actual concrete class that wraps the coroutine. Okay? In the documentation, you'll sometimes see them use the words future and task. You sort of mix them up, but they're basically talking about the same thing. Now, even though you don't have parallelism, even with just concurrency on a single thread, you still have synchronization problems, where if two coroutines are trying to manipulate the same data structure, right, they can easily corrupt the data structure. So the Async IO thing gives you all kinds of synchronization tools, mutexes, semaphores, synchronized queues, that kind of thing. So they're all available. All right. And then the final step is moving data around, right? So in order to move the data, you need a transport. So the transport is like a socket or a file handle or a pipe, something like that. Okay, some low-level operating system mechanism for reading or writing bytes. The protocol is a higher-level thing that says how are you going to use that transport. So HTTP, SMTP, DNS, what is it called? Subprocesses, right? Oh, here's the list. Yeah. Subprocesses, signals. Okay, so all of those things are supported at the protocol level. Of course, the transports need to be asynchronous, otherwise this whole thing won't work. Now, for some reason, in order to create these sorts of transports, the event loop itself has a whole bunch of methods for creating these things. So if you want to open a connection, right, there's a method for that. If you want to run a subprocess, like you want to execute some command line program within Python, there are commands to execute subprocesses. Okay? All right. So here's our first example. And let's go through it line by line. Obviously, import the IO library. This function is very simple. All it's going to do, ignore the loop. All it's going to do is iterate from from 0 to 9 and print hello world. And so there's really nothing interesting going on here. Here is the command to get the default event loop class. Okay, so asyncio.get event loop. So you always do this. Now you get the loop, the event loop. So they have some methods on the loop. Actually, they have a million methods on the loop, the event loop. But some of them are a way to schedule when to call a function. So call soon means, call it as soon as possible. They have a call, I think they have a call later and maybe a call delay. So, call it after, 5 minutes have passed. Okay. So here I'm going to use call soon to say try to run this as soon as possible. I register the function hello world, and then any arguments, 0 or more, go after that. So I'm passing in one argument. Okay. So this doesn't actually call it. It just schedules it to be called. Okay. So now the loop knows that one of the things it needs to do is call hello world. Then you say loop.runForever. So run forever means to just keep running this event loop, even if there's nothing to do, just keep running it until someone tells you to stop. And that's why in the hello world program, the last thing I do is I get access to the loop by passing it in, and I tell the loop to stop. Once it stops, it's finished. Okay? So notice that this function is not a coroutine. It's just a regular function. Okay? So I can run this code over here. So let me increase my font. Okay. All right, it's not super exciting, but so Python 3 aio hello.py. Okay, just to prove that it runs. Okay, so hello world and then finished. All right, so that's a really, really simple thing, but you can start scheduling functions to run at different times. Okay, so now we want to do something more interesting, where we have two functions that run interleaved. So we have a goodbye over here, import async IO, and we have a goodbye world and a hello world, right? So the hello world is similar to the previous one. Goodbye world is the same thing, but goodbye, okay? But there are some extra bits to it, so let's see what's going to happen. Over here, we do the same thing. The code just continues, okay? So here, get event loop. Now we have a loop. Then we say asyncio.async hello world. What this is going to do is register the hello world coroutine as a task. So it converts it to a task, okay, and registers it. Same thing with goodbye world. It registers the task, and you get a task object over here. Then it says run forever. All right. So these two methods are registered, and now the loop is going to run forever. So what it's going to do is it's going to call hello world, come over here, print hello world, but then it gets this command, yield from asyncio.sleep for 1 second. Okay? So the yield from is critical, because if the function doesn't yield, then nobody can stop it from running in an infinite loop or doing whatever it wants. It'll hog up all the CPU time. So in this case, when you say yield from, it returns back to the event loop. And the event loop now can decide, of these two coroutines, which one do I want to run? So obviously it'll choose the next one. Then this thing will run, it'll print goodbye world, and it will yield, right? So every time a function yields, the event loop then can choose which coroutine to run. So it's absolutely important that when you're writing asynchronous code, you're always yielding every time you do an I/O operation. Okay? And that gives the event loop a chance to schedule another coroutine. All right, so let's take a look at this code. And this should be in... Yeah, this one. All right, and you can see that it's pausing for a second, and then it prints them out, but notice that they're interleaved. All right, now once it printed it out 10 times, it's stuck here, right? And the reason is we have run forever. And remember that run forever will continue running until somebody says stop. But in this program, nobody says stop. Okay, so we're stuck now on the event loop. So the only way out is Control-C, and we get a keyboard interrupt. Okay, and it's basically stuck in this run forever command. All right, so the next step is what? No. I had another version of this code. Let me pull it up. All right. So here's the same code. Goodbye world, hello world. What I want to do in this case is also I want to wait for someone to hit a key, like if I, basically hit any key to stop. So if anybody hits a key, then I want this whole thing to stop. All right. So let's go line by line and look at the code. So this part we already saw, right? Mark it as a coroutine because that's required by the async IO. And then you do a yield from in order to give control back to the event loop so it can schedule something. All right. Same thing for hello world. Here's the wait input. So the wait input, it says, it assumes that everything is finished, right? And it says print stopping. And then in order to stop, it calls cancel on any tasks that are currently running. And then it tells the loop to stop. Okay? All right, so then we get the event loop, because we always need that. We register the two functions, hello world and goodbye world. But now look. We're going to call add reader to register another event, okay, or waiting for another event. So add reader is a way to say, I want to wait on a file, like a file ID, okay? So for the file, I'm going to do standard input in Python, and that comes from the system library. If there's anything that shows up on standard input, then call the wait input function, which is right here, and pass in the rest of it are arguments that get passed in. The first argument is going to be my actual loop, get event loop, because that's the only way to call stop. The second argument is going to be a list of the tasks that I have registered. So that's going to be up here, tasks, and that's how I iterate and cancel all the tasks and then call stop. Then I call run forever, and then hopefully when it exits, I call close and print finished. Okay, so let's try that out. And that was Python. Sorry, 3 AIO. There. So as soon as I hit a key, it interrupted the event loop, which canceled the two tasks and cleanly finished, right? Stopping, finished. So the idea is that if you don't use the async library, then the only way to stop a running Python program is to hit Control-C, right, to break it, and then you'll get a exception, right? So in this case, you can actually, what we're doing is, the add reader is actually waiting on the standard input event, and as soon as I hit a key, it calls wait input, cancels the tasks, and then stops the loop, which causes run forever to end, closes the loop, prints finished. Okay? Now you can see that writing this kind of code is really, it takes some getting used to, right? I mean, let's try, for example, this asyncio.coroutine. We could try to cause a few errors here. So what happens if I comment one out? So I don't mark it as a coroutine. What sort of error will I get? Nothing. And, oh, I hit Control C, my bad. Let me just prove that it still works. Yeah. Okay. So the reason that I don't need this marker here, I mean, it's a good idea to add it, but I don't need this marker, is because the async command here, it will convert any function into the appropriate, future object. Okay, so if it's a coroutine, it converts it to a future. If it's a regular function, it converts it and registers it. Okay. All right, so let's try something else. What happens if I don't cancel the tasks? And so instead of canceling the task, all I do is just tell the event loop to stop. Okay, so if you look up here, it says stopping and finished. Everything was okay. However, the Async IO system now complains that a task was destroyed, but it is pending. Okay, and so here's the hello world, right? And what they're saying is that you're ending the event loop, but there are still things in the event loop that are not finished yet. So it's giving you an error. Here it is again. Task was destroyed, but it is pending, and this time it's for goodbye world. Okay. So if you don't properly cancel it, then the library says something bad must have happened, so it raises an exception and warns you of what's going on. Okay, so it looks like we need those. Let's see, what else? Yeah, I think that's good enough. Okay, so now let's do a client-server application using sockets. So let's take a look at the client. So import the library, mark this as a coroutine. So this is going to be a call. This is the client side, which is going to call a server, right? First, let's jump down here and just make sure we know what we're doing. Get event loop. What that's going to do, it gets the event loop. That's fine. Then async says, given a function, turn it into an async object, like a future or something, and then run forever and then close, right, when it's done. So over here, when we do call server, here it's a while true, so it's basically going to run forever, which we can fix later on. But here is a magic command, yield from asyncio.openConnection. Okay, so openConnection just says, so this is localhost, and this is the port number that I'm going to use. Okay, but why the yield from? Because when we open the connection, that is a blocking call, and we don't want to wait for it. So we immediately yield from it, because if this were a more interesting program and I had lots of different coroutines registered, then the event loop could go and get other stuff done. And then whenever the event loop discovers that the connection is now open, then it will go back into this code and it will grab the reader and it will return a reader and writer object so that you can read and write from this socket. All right, so we're going to send a message, and I'm attaching a number to it so I can keep track of the messages. So hello from client, and then I take the number and convert it into bytes and concatenate it here. So I get a byte array. And I say writer.write message. So that will write the byte array onto that open connection to the server. Then we do another yield from. Again, because the read operation is blocking, right? So this says read up to 100 bytes. However, since this is blocking, we do a yield. So it registers the read with the Async IO library to say I'm waiting for some data to show up on this socket connection. But then it gives up control. Again, the event loop can do whatever it wants. Run a dozen other things. But as soon as that read operation becomes available, then, well, not as soon as when it becomes available, then when the event loop gets around to it, it'll come back over here, grab the data, and you can print it out, and then you can do another. So I added another yield from just to slow it down. So it sleeps for half a second, and then it goes back in the loop and keeps going forever. Okay? All right, so that's how you open a connection, you write to it, and then you read from it over there. Here's the server side. Okay, so we have this handle client, which we'll get to in a minute. So get the event loop, and then they have some special methods on Async IO, functions for launching server-side code. So this one is called the start server, and this thing says, okay, listen on localhost this port number. And whenever somebody makes a connection on that port, execute the handle client coroutine for each client connection. All right. So if 100 clients call, it'll create 100 handle client coroutines. Okay. So that gets turned into a future. We're running the server. This time, we're going to use a different command. This might be a typo. I don't think I need the run forever here. Anyway, run until complete. So run until complete is going to run the server. No, this is okay. Yeah, run until complete will register the server and say run it until it's completely finished. And then run forever will just keep the start server here. It'll keep it going. All right, so let's look at the code. All right, so over here, I'm going to run the server first. All right, so the server's running, and now what I'm going to do is come over here, and let me do this the other way around. Okay, so now I'm going to run the client. It'll be AIO client pi, and let me get the other one. I'm going to run two clients. Okay, so let me hit enter, and enter. All right, so I have two clients calling into the server. The server is just getting these numbers to indicate, which, not really which client, but which particular client message it's working on. Yeah. All right. So that's a pretty simple way of writing a server. So let me stop these. Notice that both of them complain. Task was destroyed but is pending, because once it gets the keyboard interrupt, it kills the event loop, but the event loop then complains that there are still tasks that need to run. Same thing here. No, this one didn't complain. Yeah, this one just died. Okay. All right. So when you start a server, they understand a bunch of different protocols. So you can open up a web server, and they also support SSL. So if you say, SSL, if you turn SSL on, which is an optional argument on the start server command, then you can support, SSL web requests, using the Async IO system. All right. So as an example of a library that you would rather use instead of Async IO. So this is a library that is aiohttp, which is built on top of Async IO. Now and this is for making let's say client-side web requests, right? The get, puts, deletes, and all that sort of stuff. Normally in Python, people use the request library. That's the most popular one. However, the request library, as it says, is blocking. Okay, so they have written or have modified the request library to make it non-blocking, but that implementation uses G-events, which is one of those async libraries that I mentioned before. Right? The name of this library is called G-requests. But the goal is that if you want to do something that's non-blocking, instead of using one of those other libraries, there's now a standard library, Async IO, that you should sit on top of. So hopefully requests or somebody with that project will rebuild their library to sit on Async IO for Python 3.4. And in fact, the Async IO library is designed to make it easy to move your code from one of these older libraries into Async IO. So anyway, that's what this library aiohttp is for, and we can just look at the code. To see an example of how it works. And so here is a client example. And you import Async IO, you import aiohttp, right? That's the one we want to use. It's basically you doing the same thing. So you say that this thing is a coroutine. Down here you say async io.get event loop, right? That's how you start. You always start with get event loop, and then run until complete. So that means run this particular coroutine in the event loop until it's finished. Typically what will happen is that this coroutine might call other coroutines that will then get scheduled, right? So, there is a use case for run until complete. And once you get that back, you'll get the content and you can print it out, okay? So get event loop then, this run until complete will call fetch page with the URL, and it'll say make a GET request to that URL. However, do it in a non-blocking way. Okay? And therefore, you'll yield from. So once you yield from, it goes back to the event loop and schedules anybody else who needs to run. Of course, if there's nobody who needs to run, then the event loop will just sit there doing nothing. Right? So in isolation, this is not that great. So anyway, you yield from, then the event loop will get a signal that we've got a response from the server. Once they get the signal, they come back over here, complete the request, get the response, and then do a yield from response read, because the read command is also blocking. So it will yield, and then once it comes back, it'll get the value. Once the value arrives, it'll get it and return the value, and that will be the content. Okay. This is a server example, but there's a better example on the bottom here. I just saw it. Well, maybe this is good enough. Yeah, so if you had a command where you wanted to run a whole bunch of commands, I mean, they're just doing it on the command line, or sorry, the interpreter. But so you can do put, delete, post, all of those commands are available. And whenever you do it, it actually gets executed, and then they tell the operating system, let me know when you get a response from the server that thing completed. So when you make these calls in a row, if you were to put these all in a row, then all of these calls will get executed, and you can just come back and get the data as soon as it's arrived. So as soon as the put gets data, when it comes back, you come back and you get the data. As soon as delete arrives, you can go back into the code and get it. Okay? Resume from the code. Yeah, okay. All right, so as I showed you before, there are lots of libraries that are being developed to sit on top of Async IO to give you asynchronous access to all kinds of mostly external resources: databases, caches, file systems, web frameworks, all of that stuff. All right, and then finally, another cool thing that's coming is, which we don't have time to go into detail with, but async and await. Okay, so this is coming in Python 3.5, and it is supposed to be a slightly simpler way of writing concurrent code. And for the first time ever, you will now, I'll just show you real quick. If we take this thing right here, right? So right now you decorated asyncio.coroutine. With this thing, you would say async. Okay, so this is, I think, this is the first time that Python has added a keyword in front of the function as a way of declaring what the function is. And then instead of using yield from, you would use await, like so. All right. So I don't know if it actually makes things easier. Maybe not, because you still have to use the get event loop. You still have to register the functions and get the loop running. You still have to stop it if you want to stop it. But async and await have some slightly better syntax for when you're actually writing your code. All right. All right. Part of the motivation for using these keywords is that it's been in C# for a while now. A lot of other languages are picking them up. I think that JavaScript is considering adding it, and that's a major language. And so, in order to keep the programming style consistent and with other languages, so that people who learn it in one language can use it in a different language, it looks like they want to adopt these keywords to help with asynchronous code. All right, so that is it. So that's the wonderful world of Async IO. It's kind of messy, but once you get the hang of it, essentially it boils down to get yourself an event loop, register all the coroutines that you want to execute on the event loop, and then run the event loop. And once it starts running, it will just, whenever it blocks on I/O, you will yield from that function, and it'll try to run a different function. Right? So if you give it 20 functions, it'll just keep bouncing around those different 20 functions, trying to get work done, and blocking on I/O and jumping into somebody else's code. And hopefully, when hopefully it never runs out of stuff to do. that data arrives on a server, data arrives from file system, and your code will just jump into that and keep working. All right. In fact, this whole thing is basically Node's claim to fame is how they handle asynchronous processing. Their coding model is kind of nasty, but they were able to get tons of work done, because they could jump from one event to the other. So with Python, the programming model is easier. You now have the same. Now you have a standard library which gives you the same sort of processing model, and hopefully with async await, it'll be slightly easier to write those programs. Okay. All right. Well, so this has been a quick intro then to Async IO. It's super complicated, so we've just sort of gone over the tip of the iceberg. But definitely try to use, maybe you don't want to mess with this directly, but try to use libraries that are built on top of this so that you can benefit from this low-level behavior. All right. There's a question. Will you share the slides? I think we can. We have the video for this talk will be up on the Developmentor site. If you go to develop.com, maybe /webcasts, and I can make it available, and we can see if we can put a link up on the website. All right. Well, if there are no other questions, then yeah. So if there are no other questions, then good luck with asynchronous programming. It's actually super hard to do well, and it'll take quite a bit of practice before you get used to it. So, but at least the facilities are there in Python.